Hello, sir. Hello, classmates. Today, I'll be sharing my learnings from the review article, a brief review for chemical looping combustion as a promising CO2 capture technology, fundamentals, and progress. This paper is a collaboration between two universities from China and Sudan. It's relatively new, given that it's published in 2021 in the journal Science of the Total Environment. To give a brief background about this paper, since the Industrial Revolution, we have been using fossil fuels, and we are using it excessively, regardless of the consequences, because of its high economic value. However, we know that fossil fuels harm the environment because of their high CO2 emissions. In fact, fossil fuels contribute to 75% of the anthropogenic GHG emissions. And also, fossil fuels are non-renewable sources, and studies show that it will run out around the 21st century because of our high consumption rate. In the mid-20th century, humans took note of this problem. And as mentioned during our class, in 1997, the United Nations made an agreement known as Kyoto Protocol, and this was to reduce the GHG emissions. It was later re-examined in the Paris Agreement in the year 2016. And in the Paris Agreement, the consensus was the allowable maximum CO2 concentration in the atmosphere is 450 ppm, but it already exceeded 400 ppm in the year 2016. There are three leading solutions that have been presented. The first one is absorbing the existing CO2 from the atmosphere. An example of this would be the one which I shared in the article 1, which is biochar. It's used to absorb CO2 from the atmosphere. The next solution is expediting progress toward renewable energies. However, this is difficult to do immediately because renewable energies are more expensive than fossil fuels. Lastly, carbon dioxide capture and storage, or CCS. Since it's most likely that we will still use fossil fuels, at least in the next decades, uh, while we keep innovating to make renewable energies cheaper, research on CCS is very important to control CO2 emissions. These are the common CCS techniques categorized according to capture option: post-conversion, pre-conversion, oxy-fuel combustion. So some examples are absorption by chemical solvents, adsorption by solid sorbents, and these are actually discussed in our class. And then we have membrane separation, cryogenic separation, etc. The CO2 capture and storage principle is to produce energy from hydrocarbon. And then during combustion, separating carbon dioxide from the stream of combustion gases or flue gases, then compressing and storing CO2 away from the atmosphere. Over the last 3 decades, these technologies underwent massive development and they even passed to commercial utilization. However, the main drawback is that they have lower efficiency and high energy penalty. Thus, the current market does not encourage or support their utilization. Therefore, great efforts have been made in the last 2 decades to reduce the energy penalties associated with capturing technologies. And among these efforts, we have chemical looping combustion, or CLC. It is a CO2 capture technology with a low energy penalty. When we say low energy penalty, what does it mean? Well, energy penalty refers to the fraction of fuel that must be dedicated to the capture technology for a fixed quantity of work output. For example, it can be the additional fuel required to maintain a power plant's output. And the key to CLC, or chemical looping combustion, is keeping all the air out in the reactor where the fuel is combusted. Hence, there is separation of carbon dioxide from the nitrogen gas. And we know that our air is composed of 79% nitrogen. And because CO2 is inherently captured, it has lower energy penalty. It even has the potential to be the cheapest capture technology with high efficiency up to 100%. Just a trivia, the first who introduced the term chemical looping combustion was Ishida et al. In 1987. The picture on the right shows the chemical looping combustion, and we will discuss the details of the process in the next slide. So how does chemical looping combustion work? In the heart of CLC, we have two fluidized bed reactors. We have the air reactor and the fuel reactor. Fine metal particles called oxygen carriers are used to transfer oxygen between the two reactors. So in this diagram, the oxygen carrier is designated by this MEOA or MEOA-1 or ME. The oxygen carrier is supplied to the fuel reactor to combust the fuel. Hence, it's a reduction reaction because the oxygen from the metal oxide or the oxygen carrier is used to combust the fuel. And then it's looped back to the air reactor where it undergoes oxidation reaction. So from Me or MEOA-1, its oxygen is replenished to MEOA. And it's cycled back to the fuel reactor to combust the fuel. So in the air reactor, oxidation reaction happens. And in the fuel reactor, reduction reaction happens. Hence, this is a continuous chemical combustion process taking place between pure oxygen and fuel. As a result, the flue gases do not contain nitrogen gas. There's an additional step here called oxygen polishing. So in the case that we want to complete the combustion process, in case we have carbon monoxide and H2 in our stream, pure oxygen is introduced into the flue gas stream so that still CO2 and H2O are the main products of the combustion. And the last step is separating water from CO2, and that's easily done by condensation. CO2 is then compressed and stored. Comparing this process to other CO2 capture technologies, the main advantage of CLC is the inherent CO2 capture without energy penalty for the separation process. Let's watch a short video for an animated version of the CLC process.
In the chemical looping combustion process, air and fuel do not directly mix or react. The oxygen required for fossil fuel combustion is provided by a solid material such as iron oxide or copper oxide. These solid oxygen carrier materials are continuously circulated between a fuel reactor and an air reactor. In the fuel reactor, the oxygen carrier supplies oxygen to burn the fuel. In the air reactor, the solid oxygen carrier reacts with air to renew its oxygen content. After the oxygen carrier is oxidized in the air reactor, it is transported through a cyclone to separate the solid oxygen carrier from the air. The oxygen carrier is recycled to the fuel reactor to complete the cycle, or loop. The flue gas from the fuel reactor is a mixture of carbon dioxide and water. The carbon dioxide can be recovered by simply condensing the water vapor. NETL's chemical looping.
The next of the slides will discuss the CLC process when different fuels are used in terms of whether gaseous, solid, or liquid. First, using gaseous fuels. For gaseous fuels, the reaction between the oxygen carrier and gaseous fuel is straightforward, and it's actually a solid gas reaction. There's no problem in fluidizing the fuel reactor because the fuel itself serves as the fluidizing medium. The common fuels used are natural gas, which is composed mainly of methane, syngas, composed of hydrogen, carbon monoxide, and carbon dioxide, and pure methane. And the common metal carriers used are nickel and cobalt. However, later on, they shifted to using copper and combined oxides or natural ores for environmental concerns. The slide also shows the reaction involved when using gaseous fuels. So the first reaction is the oxidation reaction of the metal carrier or the oxygen carrier. As you can see from OA minus 1 is oxidized to MEOA by the addition of an oxygen atom. And then the rest of the equations show the possible reactions in the fuel reactor, which is the conversion of the fuel into carbon monoxide or hydrogen. And for the complete reaction, the conversion of the fuel to carbon dioxide and oxygen, while the oxygen carrier is reduced. The first CLC unit using gaseous fuels was actually installed in Chalmers University of Technology in Sweden. It was the year 2004. It was a 10 kilowatt thermal unit. In the same year, another unit was built in Korea, this time a 50 kilowatt thermal capacity in the University of Institute of Energy Research. Up to date, 20 test plants were built worldwide for gaseous fuels, ranging from capacities of 0.2 kilowatt thermal to 1 megawatt thermal. And in the countries Spain, Austria, France, Germany, China, Japan, and the USA. Now let's move on to solid fuels. Since coal is abundant and involves plenty of CO2 emissions, it's an excellent choice for CLC. Another option for solid fuels is biomass, and we can use it for sustainability to achieve neutral CO2 emissions. Since the CO2 in the burning of biomass has already been absorbed from the atmosphere during photosynthesis. However, the disadvantage of using solid fuels, unlike in gaseous fuels, is the reaction between a solid fuel and another solid, which is the oxygen carrier. It's a slow solid-solid reaction. Hence, two solutions have been presented. The first is in situ gasification, chemical looping combustion, or IG-CLC, and another is chemical looping oxygen uncoupling, or CLOU. Let's first discuss IG-CLC. It works by gasifying the fuel reactor, and this is done by recirculating part of the fuel reactor exhaust. So in the exhaust of the fuel reactor, we have water and carbon dioxide. We recirculate it to serve as the gasification agent. But there is a disadvantage. which is the escaping of char particles to the air reactor. And the result is uncaptured CO2. The reactions for this technique are shown. Let's discuss them one by one. The first reaction is the pyrolysis of the solid fuels, resulting to products volatile matter, which is composed of volatile carbon, combined water, net H, nitrogen, and sulfur. And the other product is char. So this is the solid fuel. The products are volatiles or volatile matter and char after the pyrolysis. And the next two reactions are char being gasified into hydrogen and carbon monoxide. So this is char, and after gasification, it becomes hydrogen and carbon monoxide. The last reaction shows the combustion using the metal oxide. So this time, the products of gasification, which are hydrogen and carbon monoxide, and the product of pyrolysis, volatile matter, goes into complete combustion to produce hydrogen and carbon dioxide. And of course, our metal carrier or oxygen carrier is reduced. So in this diagram, the reaction between the char and the volatile matter, the reaction between carbon monoxide, hydrogen, and the volatile matter with the oxygen carrier now produces complete combustion products. Let's move on to the second technique in using solid fuels for chemical looping combustion. It's the chemical looping oxygen uncoupling or CLOU. It actually solves the problem in IGLC, uh, which is the char being entering the air reactor and causing an uncaptured CO2. And this is done by using specific oxygen carriers such as copper oxide, which releases oxygen easily at high temperatures. CO2 is also recirculated for fluidization, but no gasification step is required. These are the reactions for CLOU, and let's discuss these reactions one by one. Similar with the previous technique, which is IGLC, the first step is the pyrolysis of the solid fuel into volatile matter and char. The second step is the differentiating step between the two, which is the uncoupling of the metal oxide. As you can see here, oxygen gas is produced from the uncoupling of the metal oxide. And the rest of the reaction are actually normal combustion reactions. So the char, which is the product of pyrolysis, undergoes combustion reaction by the addition of oxygen, and then the rest of the products, hydrogen, carbon monoxide, and volatile matter also uh, undergoes normal combustion reaction. So char reacts with the oxygen, the char reacts with the O2 from the oxygen carrier. Even the volatiles react with the O2. So again, the differentiating step between CLOU and IGLC is that O2 or oxygen gas is produced in CLOU. The main parameters that affect the performance of chemical looping combustion using solid fuels are the following: the type of oxygen carrier, the reactor temperature, the circulation rate, the H2O to CO2 ratio, the fuel rank, the pressure, and the design. And the impact differs between the two techniques between IGCLC and CLOU. For the interest of time, we will not discuss the effects one by one. But for example, a high reaction temperature is preferred in IGLC since it favors gasification and reaction between the oxygen and the fuel. On the other hand, CLOU is more sensitive with the reaction temperature since the oxygen coupling is dependent on the reaction temperature. The first continuous installation of CLC using solid fuel was in 2008 at Chalmers University of Technology in Sweden. Again, it's a 10 kilowatt thermal capacity unit. The next installation was in 2009 at the Southeast University in China. It's also a 10 kilowatt thermal unit. The picture on the right is actually from a different university, from Huazhong University of Science and Technology, also in China. And it shows the development of the CLC reactor from the year 2011 to 2017. The first CLOU unit was built in the year 2012 at the Instituto de Carboquímica in Spain. It was a 1.5 kilowatt thermal unit. Now let's move on to CLC using liquid fuels. Up to date, most CLC research is focused on solid and gaseous fuels, and only a few studies have been conducted on liquid fuels. This is because we don't usually use liquids in stationary combustion units because they are mostly for transportation. And the main challenge of liquid CLC is our inexperience in utilizing liquid with a fluidized bed reactor. There are two proposed processes to solve this issue. The first one is fully evaporating fuel before introducing to the reactor, and the second one is direct injection in the reactor. The reactions in liquid fuels are the same with gaseous fuels. Next, we will discuss the oxygen carriers. An oxygen carrier must satisfy the following criteria. It must have high oxygen transport capacity and a great thermodynamic and kinetics capability of converting fuel to H2O and CO2 in the CLC operation. It's obvious that the first two is important for the success of the combustion reaction. The next is it must have high melting temperature. This is required since melting will cause the metal carrier to agglomerate or clump together. Since the CLC system operates between 600 to 1200 degrees Celsius, the metal carriers cadmium, zinc, cesium, and molybdenum are avoided. However, copper, which has a relatively low melting temperature at 1085 degrees Celsius, it's commonly used, hence the reactor temperature must be maintained below 900 degrees for a stable operation. The next characteristic is excellent fluidization characteristic, meaning it's not agglomerating in the system. Unfortunately, copper is known to agglomerate. An oxygen carrier must have high mechanical strength to attrition and fragmentation. And an example of this oxygen carrier is nickel. However, nickel is toxic. Copper and manganese unfortunately have short lifespans. The next is it has no ability to carbon deposition, thus avoiding release of CO2 from the air reactor. And the last two criteria are very obvious. It must be low cost and it must be safe and environmentally friendly. An example of a toxic oxygen carrier, as mentioned, is nickel and also cobalt. Iron is cheap and environmentally friendly, but it has thermodynamic constraints. Finding a metal oxide that could accomplish the criteria mentioned is not easy. Even oxides with excellent fluidization properties and thermodynamic capabilities could not endure a long time. So the effect is a decreased reaction rate after a few cycles. Therefore, supporting materials are introduced. Examples are aluminum oxide, titanium dioxide, silicon dioxide, zirconium dioxide, and magnesium aluminate. So, they are introduced to increase the mechanical stability of oxygen carriers. The table shows the most common oxygen carriers used in pilot plants. So these are nickel, iron, copper, cobalt, manganese, and we also have combined oxides. These are manufactured transition materials. For the natural ore, we have iron, ilmenite, manganese, and calcium sulfate. The values on the right show the total experience in hours in using these oxygen carriers. So we have the most experience using uh, nickel at 20%. Next is using ilmenite at 18%, followed by iron and copper. These are scanning electron microscopy images or SEM images of the oxygen carriers. The first three are nickel oxide and the bottom pictures are ilmenite. For the conclusions and future outlook, chemical looping combustion is an economic carbon dioxide capture technology. Gaseous, solid, and liquid fuels can be used in chemical looping combustion. Negative emissions can be achieved by using biofuels. Developing an oxygen carrier lifetime is a key issue in chemical looping progress. So that's the main challenge currently faced by the CLC technique. It's the oxygen carrier lifespan. But it's still recommended for commercialization, and the author also recommends to conduct LCA on different CLC scenarios. I would like to end with this graph, which shows the annual CO2 emissions from fossil fuels and cement production. And this is global data. The y-axis shows the CO2 emissions in gigaton per year. We cannot deny that the anthropogenic contribution to CO2 in the atmosphere is very significant, as shown as the jump from 1850 to 2010. So from almost zero, it jumped to 30 gigaton, more than 30 gigaton per year. If humanity cannot shift to renewable energy, then we must find and implement ways to capture carbon dioxide from the combustion process. And chemical looping combustion is one technique that provides low energy penalty and high efficiency. Thank you very much. I will now answer your questions.